Hello, I'm Renard, and I'm presenting Tailoring Programs for Static Analysis via Program Transformation. So static analyzers are a popular choice today to automatically find bugs in code, and there are some great open source tools available, like the ones that I've put here on the slide. Now, we know that static analyzers approximate, and one familiar trait where they approximate is at a theoretical level. So there are standard issues around decidability, whether we can find or detect certain bugs, and to what degree we can be precise about finding those bugs. But static analyzers also approximate in the interest of practicality. So when an analysis is implemented, it may not understand the complete, every construct of a language, or it might miss some function models. For example, the analysis might not know that a particular function closes a file if it fails to infer that behavior, or if we don't specify it. And an interesting consequence of this approximation is that developers will sometimes change their code around the analyzer limitations. And so to make that very concrete, here is some code from a logging utility where a developer annotated a code change by saying that this is a Clang static analyzer workaround. And although I can't elaborate deeply on what's going on here, and there are more details in the paper, the basic gist is that by pulling out a string constant from a string compare function, it prevents a macro expansion. And this macro expansion would otherwise cause a false positive to be raised. And so this developer performed this change, and it prompts the question, why fix an analyzer issue in this way? And we make the observation that analyzers have various knobs, various settings to tune the effectiveness of that analyzer for a particular code base. But these analysis knobs are often insufficient. The prevailing ways to customize or configure an analysis is by using some set of command line flags, or suppress certain checks with code comments that you can put in your code. And the thing to realize here is that analysis authors implement these knobs. So as an analysis user, you're really kind of at the mercy of the settings and options available to you. And if these don't address an underlying issue, you'd have to go about a very complex way to kind of find a solution. But so one way to work around that complexity is by changing your code. And analysis users can modify their programs to change analysis behavior. And so we can look at program transformation as an analysis knob in some sense. And that's really the key idea behind the approach of our work. It is to automate an approach that is otherwise manual and ad hoc to prevent certain analyzer limitations from cropping up. And so in our approach, we tailor analysis via program transformation. And the first step to enabling this process is a way to change code, a way to change program syntax using declarative templates. So to go back to this original example, we can express this code transformation as two patterns, two templates that match certain properties of the syntax. So here there's some highlighted code of holes that will bind to the underlying syntax, and we'll rewrite this fragment and pull out that constant string in the same way that the original change does. Now, the tooling associated with our approach is a tool called Combi, and you can find more information about Combi online. The general takeaway is that it is a lightweight way to declaratively specify a program transformation that supports many languages. It's very fast, so it works on large programs, and it's more expressive than regular expressions. So it's actually developed to help use cases where we want to change code and not just text. So in addition to an approach for rewriting programs and expressing these transformations, we also developed this idea of temporary modification to the program. So our approach does not advocate for changing the program permanently for an analysis, but rather as a pre-processing step, ideally that tailors that specific instance of the project to an analysis to avoid, for example, false positives. And so in our evaluation, we aim to show that tailoring programs in this way can improve static analysis. And so we chose 5 analyzers across 3 languages to kind of demonstrate the generality of the approach. I've put them here on the slide. And we identified long-standing issues on GitHub where developers reported using a tool and then a false positive associated with that tool. And we identified these through keywords that we ran and performed a commit search. So our results show that we run our approach across all of these projects. And I just want to point out some high-level takeaways. So one is that we ran our approach on very large projects, so up to hundreds of thousands of lines of code. And we showed that it's efficient. When analysis takes in the order of minutes, performing this pre-processing step, this rewriting of particular patterns, takes only a couple of seconds. So it's feasible to perform this step and process at a large scale. One example that we show is that we can prevent a false positive from being reported by changing the code where it's not modeled that a particular socket is closed. And a very interesting property of our approach is that we can reuse the templates and patterns that we identified to prevent false positives and search for them in other projects. And so we found other instances of false positive inducing patterns that we could reuse and prevent in other projects. So the key takeaway is that these local targeted transformations can improve static analysis without adverse effects. I'll summarize the talk with a summary slide that you can look at, which covers the key points of this presentation. Thank you for listening.